Hey everyone, in this video we're looking at waves as they travel down a string, so kind of a particular application of waves, though we're still going to go back to some of the things we've learned. The wave speed equation, interference, all of those will come back as well. So we really just want to talk about a lot of things very quickly, pretty briefly. So first thing, let's get right to it. Wave reflection. We're all familiar with waves reflecting. When you see yourself in a mirror, light waves are bouncing off the surface of that mirror. If you've heard an echo, that's another example of, this time, sound waves bouncing off and returning to your ears. Waves on a string can reflect as well. They are not reflecting off of other waves, however. Remember, waves don't bounce off of each other. They interfere, right? And then they keep on moving as they were before. But if I have a piece of string like I have here, attached to a wall, and I flick my wrist, so to speak, so I make this wave pulse that's traveling down and to the right. It's moving to the right, of course. What that means is when it reaches a particle, like if I look at this particle on the string right here, well, when the wave gets to it, I don't know why my little particle's disappearing on me, but when that rope gets to this spot right here, it's going to apply a force. It's going to make that particle move upwards, all right? When it gets to this piece right here, it's going to apply a force, make that particle move upwards, and then it's going to get right here. And it's going to apply a force on this particle, the particle that's attached to the wall, and it's going to apply a force upwards. But because right here the particle is attached to the wall, that means the wave is applying an upward force on the wall. And we should all remember what happens when one object applies a force on the other object, or on another object. When the wave applies an upward force on the wall is going to apply a downward force back on the rope, which means that all of a sudden there's downward forces on this string. It's going to happen every time that wave pulse passes by, every time that wave pulse applies an upward force. So what we have is as that wave hits the wall, it's going to reflect, it's going to bounce off, but it's going to get inverted because the wall keeps applying an oppositely directed force. So this is our first key idea. When waves on a string hit a boundary, yeah, they're going to reflect, but if the boundary is secure, if it's solid, or if it's, another word, a fixed barrier, a fixed end, that wave gets inverted due to Newton's third law. I can show you that with a quick little visual here. Let me put it on slow motion. I'm going to send this wave pulse. It makes these pieces on the string move upwards, but this piece is attached to the clamp. Therefore, it gets inverted. It applies a downward force, so the wave flips. And the same thing is happening on this side. Okay, so that's our example. The wave bounces back, but in this case, it gets inverted. What if, however, instead of having this solid clamp, I had this loose end? Well, now as that wave approaches, the string is attached to this ring, which is able to easily slide up and down. It's not welded to this pole. It's not attached securely. So I don't have the same issue of that string interacting with another object. This ring, we'll assume it's frictionless, just keeps sliding on its own. So I don't have forces applied on other objects. Therefore, I do not have an example of Newton's third law when these waves meet a loose end. That's kind of the term. They still reflect, they still bounce back, but they do not invert. So that's our second diagram right here. Here I have that wave pulse coming in. It's again applying upward forces. It's still going to apply an upward force on the ring, but there's no other object for there to be an equal force back in the opposite direction. So the ring just goes up and down like before. So our result is a reflected wave pulse that's on the same side. So it is not inverted as long as we have a loose end, the opposite of before. Fixed ends versus loose ends. You should know that difference. Next thing, part B, something called a standing wave. And a standing wave is really something that occurs when you have waves that are reflecting and interfering with each other. When we send waves down a string, we can usually tell what direction they're going. They're sliding to the right, for instance. But if waves look like they're standing still, that's kind of interesting. And that occurs if you have just the right scenario. Let me, in fact, go back to my simulator. if I have no end, if this wave is just going out a window, all right, let me hit play. Well, if I send one wave pulse, or two wave pulses, or three wave pulses, those waves are just leaving. They're not interacting. They're not interfering with one another. They're just disappearing forever. If I have a fixed end, though, and I send one wave pulse and then another wave pulse, when those waves are at the same spot at the same time, they interfere. Looks like we have a lot of destructive interference going on. If I have a loose end, well, I might have some, oh man, let's restart. Let's send one wave and then another wave. Ooh, there are spots when those two waves are interfering. Note though, remember, that these waves aren't flipping when they meet. This wave here keeps traveling to the right, it reflects, and then it inverts. Well, if I have a certain scenario where I make waves at a certain rate, maybe I can make it look like the wave isn't simply traveling left and right. Instead, it looks like those waves are just moving up and down. I'm not very good at it with this. Let me restart. Let's watch here. Oh, just for a moment, look at this. It doesn't look like those waves are moving left or right anymore. It looks like they're just kind of wobbling up and down, up and down, up and down. I no longer have that traveling to the right visual. Let's try with a fixed string. Let me restart. Oh, same kind of thing. Not perfect. Let me try going down to 125. I have to hit just the right scenario. I have to have just the right frequency. Oh, look at this. This is pretty good. These waves no longer look like they're moving left or right. It looks like they're just fluctuating up and down, up and down. In fact, look at this green dot here. There are times when this green dot isn't really moving at all. And obviously, look at this. Oh my gosh, this is moving up and down all kinds of amounts. So this is what's known as a standing wave. It only occurred when I had those waves reflecting and I had to have the right frequency. So that's the key idea. Reflecting waves, they're interfering with each other, and the result, what you see, are waves that aren't simply moving left or right. It looks like the waves are just standing still. This is a classic diagram. For standing waves, it's just one string, but this is showing you that that string is going up and down. I sometimes like drawing these arrows. Looks like it's just going up and down. Sorry, I can't draw straight lines. Up and down. And there are some key points on these waves. Remember those parts that didn't look like they're moving? Those are called nodes. So there's a node. Here's another node. Oops, nodes. There's another node. I guess it should just be node. The opposite, the pieces that were moving a whole bunch, like right here, and right here, and right here, those are called antinodes. They're the opposite, antinodes. Another thing about this diagram, we'll assume that the length of the string is simply from one spot to the next spot. If they say the length of string was 1 meter, they're measuring from here to here. Technically, you could probably argue that this string must be longer than 1 meter, right? Because it's actually bending and curving. But in real life, this shape is very tiny. These amplitudes are puny compared to the overall length of the wave. So just to simplify something, if they say that from here to here is 1 meter, use that as the length of the wave, and vice versa. If they tell you the length is 25 centimeters, that distance is from here to here. The next thing that's worth noting is understanding how to count wavelengths, because standing waves are really nice. If you make a standing wave, it's very easy to measure things like the amplitude because it's not moving. It's not a hot mess. It's also pretty easy to tell what a full wavelength is, because remember, a wavelength is one spot to the next repeating spot. I'm going to sketch out one wavelength. I'm going to label one wavelength. Let me flip here to maybe orange. From right here, I'm going upwards. I'm just like this. Then I keep going up and up and up. I reach a crest. I start going down and down and down. Here's a trough. Here's another moment when I'm going up. So from this spot to this spot, this here is one wavelength. One wavelength is one hill and one valley. It's very helpful to learn how to start counting wavelengths. This whole diagram, I have 1.5 wavelengths present, because I have a hill, I have a valley, and I have another hill. And that's super helpful because I know, for example, if this length of string was 1 meter, that 1.5 wavelengths in total is 1 meter. Therefore, I could just solve for lambda. A lot of math problems using standing waves require you to figure out how many wavelengths are present, and that will give you the wavelength. And then that's really easy because I can still use my wave speed equation. If I know wavelength and maybe a problem gives me the speed of the wave, I then could solve for the frequency. All right, so standing waves are this interesting kind of appearance when waves are interfering. It's very easy to measure things like amplitude and wavelength with these waves. And there are these terms known as nodes and antinodes. Okay, let's get to the last section of these notes, part C, the energy and speed of a wave on a string. First thing, the energy of a wave is based on its amplitude. There's no equation that you have to worry about. We're not going to be plugging in and solving for anything. But if I have 2 waves on a string, here's one. And then here's another wave. Let's say I make it significantly bigger in terms of amplitude. This wave here has more energy because if everything else is equal, this has more amplitude. And it should make sense. Remember, how much energy there is based on the work that's being done. And work is force times displacement. You could argue that, well, if I have a larger displacement, that must mean there's more work, therefore more change in energy. So the AP test does not expect you to know an equation, but they do expect you to know that if you increase the amplitude of a wave, if everything else is staying the same, the energy of that wave is staying or is increasing. The amplitude increases, the energy increases. The last idea has to do with how fast waves are moving in strings. First, if I have a single string, all the waves move at a constant speed. Let me get back to my simulator. I'm going to get to no end. I'm going to restart. This wave, now we clearly see them moving, right? This is not a standing wave. These waves are all sliding to the right at a constant speed, and I can tell that pretty easily because none of these waves are interfering with each other. They're just sliding to the right. Let me go to a pulse. When I send a second wave pulse, it doesn't catch up with the next one, and it looks like they're going at the same speed. Even if I decrease the amplitude, those waves move at the same speed. If I get this oscillator going and I suddenly increase the amplitude, the speed of those wave pulses aren't changing. If I set up a timer and I went start, stop, I would still get the same speed, even if I change the frequency. Yeah, I'm making more waves, but if I watched one of these crests, the speed of that crest as it's going to the window is not changing. In fact, it doesn't even change with increasing friction. Yeah, the amplitude decreases, but again, if I'm timing one wave crest moving to the right, none of these things that I'm changing, amplitude or frequency or damping, friction essentially, changes the speed of those waves. What does affect the speed? If I had 2 different waves and I had one wave I had one string with more tension, changing the tension does change the speed of the wave, as does changing the density. All right, mu, this lowercase Greek letter sigma right here, this is the density of the string. It's the linear density. This, of course, here is the tension. You're not actually expected to really know this equation. Oh, man, my screen is kind of flickering on and off. Hopefully it comes back. For the AP test, you're not really expected to know the equation that I have right here. Let me get rid of this, whatever's going on there. All right, I just have tension. They maybe expect you to recognize there's a relationship between speed and tension and density, but this is not on the equation sheet, and you won't be asked to plug in and solve for it. If I go back to my simulator, if I suddenly lower the tension, then it's taking these waves a longer amount of time to slide to the right. If I time this wave pulse, and then I reduce the tension, this wave pulse is going to take significantly longer to get to the end. So changing the tension does. This app doesn't let me change the density, but thicker waves, more dense strings, I should say, do take a longer amount of time because higher density waves, the speed of that wave goes down. Anyway, this is the main idea, or these are the main ideas for waves on a string. They reflect off surfaces. You can get something called standing waves, and you have the energy of a wave based on the amplitude and the speed based on tension and density. All right, that's long enough. Thanks for watching.